Welcome back, folks. Let's continue our discussion about some intricacies with friction force and a couple of cases to consider here, one of which deals with this object that is stationary. And the question, a common form of a question, is something about this, about to just make something start to slip or just before something starts to slide. So what they're talking about there, well, this thing is stationary, all right? And so we can push on it. Let's call that an applied force. And, well, there will be some amount of static friction force if this thing is stationary. But we're talking about what's the smallest amount of force that can make the thing move, or what's the most amount of force that can be applied before it moves. That's really the same question. Even though one's talking about it not moving and one's talking about it in the object starting to move, we're actually talking about, I'll reference yesterday's stuff, we're actually talking about this same spot in the graph, this peak here, where, you know, has this thing at this force started to move right now or not, not moved or moved? It's the same force. So what we're trying to really get at here is the concept of that there is a peak or maximum amount of static friction force that can be exerted by surface on object. All right, and well, we can figure out what that is. If this thing hasn't moved yet, or is just about to move, or has just started to move, we're really saying that these two forces are equal and opposite. All right, so that says that this thing has not yet begun to accelerate, or just at the instant before it does. Or that's, you kind of have to take. I understand that people will say, yeah, but this says it started to move. So how can acceleration be zero? Well, maybe it's the instant before that. You just have to accept that that's what we're talking about here. So what we say is our net F statement in the x direction says that A, well, minus FFS max, so many subscripts, equals 0, or that A equals this force. So how big is that force? Well, that force by definition is the static coefficient of friction times the normal force exerted on the object. Well, to complete our free body diagram, how big is the normal force? Well, the normal force, if we do a net Fy, we can say that the normal minus mg is 0, so therefore normal equals mg, because Ay is 0. So that means we can say that the friction force is mu static mg. And we know those things. Look, here's mu static. Here's m. There's g. So that's 50. The applied force is 50 newtons. Now that is the amount of force, the smallest amount of force that will make this block start to slide. Or it's the most amount of force we can apply before the thing starts to slide. You know, so 50.0001 will make it start to slide. I know it's 50, and we just said this, but again, you have to sort of take that as the same question. So if it takes 50 newtons of force to make this thing start to slide, this says, well, what if we apply 40 newtons of force to the object? Well, first of all, the question is, how much static friction force is there? And the answer is not 50. All right, you have to remember that if we push on this object with 40 newtons of force, well, if there were 50 newtons of friction force, what would this object do? It would accelerate to the left. But this object is stationary. Friction isn't going to make this object accelerate to the left. So friction in this case is only big enough to counteract the force that's applied. So in this case, this thing stays stationary, and the friction force is 40 newtons. Because remember, if we go back to the other day, come on now, bang, ding, why won't you do it? Well, why won't you do it? There. If you go back to the other day, remember this static friction force can be lots of things. Static friction force might be nothing. Right? It might be a little, it might be a little more, it might be anything all the way, all the way up to this maximum amount. So if this is 50 up here, but we're saying, well, there's only 40 newtons of force applied, how much is the static friction force? Well, it's also 40. So we have to be very careful. What seems to be the problem here, folks? You have to be very careful using this equation. This equation as an I mean, that equation is an absolute, but only when we're talking about the maximum static friction force. It's just not true to say that there's a static friction force equal to mu n. Right? That is not true. What you will see somewhere in some cases is that the static force can be, this will work, less than or equal to mu n. That's true. It could be up to mu n. It could be 0. Okay, but just be careful that saying static friction force is 50 newtons. In this case, it's not. It's only 40. So what happens? Well, nothing happens. If it takes 50 newtons of force to get this thing moving, and we apply 40 newtons of force, nothing happens. That's not enough force to get this thing moving. Here's a different case. This object, well, let's see, how much force to make it slide at a constant velocity? Well, constant velocity, there's another a equals 0 thing. Okay, so we're pushing. There's a friction force. Sliding, that means this is a kinetic friction force. I'll draw my mg. I'll draw my n. These aren't to scale. I mean, yeah, okay. So what force must be applied? Okay, well, a net F says that A equals FFK. If A equals 0, the net force is 0. Those two forces are equal and opposite. So how big is the kinetic friction force? Well, the kinetic friction force is, by definition, mu k times n. And as we said before, n in this case, via a net force in the y direction, the normal force is equal to mg. So we can say that A is mu k mg. And there's mu k, and there's m, and there's g. So the applied force required to keep this thing moving at a constant velocity is 25 newtons. Well, what if we push with a force of 40 newtons? What's FFK? Well, guess what? There is only one. There is one and only one kinetic friction force, and that is, by definition, that much. And so this is still 25 newtons. We apply a force of 40 newtons to an object where the friction force is 25 newtons, and we get something that looks like this. This object accelerates to the right. What happens? Acceleration. And furthermore, we could say that A minus the friction force, that's a minus, equals ma. Or we could actually express the size of the acceleration. That's the difference in forces, the net force over the mass. So the net force is 40 minus 25, 15 newtons over 10 kilograms. And this thing happens to accelerate at 1.5 meters per second per second. So notice, the point being, look, this same force, and by same I mean same, the same force applied in two different scenarios has completely different effects. In the static case, it's not enough to overcome that peak static friction. It's not enough to even get the thing moving. But if the thing is moving and we apply that force, it's enough not only to keep it moving, but to make it accelerate. So we have to be real careful about, what's the scenario in terms of, is something moving or not? Therefore, which coefficient are we supposed to use? Therefore, what effect does that have on object's motion? Let me circle back a bit to yesterday's stuff. When we talked about the idea, and yesterday, last time, whatever, a different video that maybe you haven't seen, we talked about this idea of mu. All right, what we didn't say is some qualitative and maybe sort of quantitative stuff about mu. There are a few important things that we should mention. Mu, the coefficient of friction, this characteristic that exists between any and every two combinations of surfaces. All right, well, one thing, notice here, mu is a ratio, right? A ratio of two forces. That means mu is measured in newtons per newton. And a newton per newton, well, is not a newton. A newton per newton is, well, a non-unit. A newton per newton is 1. So mu, so let's say facts about mu. It is unitless / dimensionless. It has no units. It is not a force. Lots of people have trouble with plain old wording when they say, what's the coefficient of friction? When a question says, what's the coefficient of friction? Some people will say, all right, well, here's what I'm looking for. No. All right, coefficient of friction is not a force. You'll never see mu drawn on a diagram because it's not a force. It's a ratio of two forces. Well, the peak static friction, that's one thing. The peak static friction is always, and be careful about using always, but in every case that you as an introductory physics student will see, the peak static friction is always more than the kinetic friction. And that's for the same normal force. And what that means is that mu static is always bigger than mu kinetic. There's always I mean, this is true physics. It always takes more force to get something moving than it does to keep it moving. Right? Here's the takes more force to get it moving than it does to keep it moving. And that's an inertia thing. All right, objects by their nature tend to resist acceleration. And so this is like a force that accelerates, that gets something moving from rest into motion. This is a force that is about maintaining motion. All right, so Newton's first law says that objects at rest tend to stay at rest, and you have to apply a net force to get them moving, but objects in motion tend to stay in motion. And so in that case, we don't need to apply more force to keep things moving. We just have to apply, quote, enough force. So that leads us to this idea, these relative values of mu s and mu k. There's always a greater mu s for any given combination of surfaces than there is a mu k. Okay, and furthermore, again, you got to be careful with these always statements, but any mu for you as an introductory physics student is going to be less than the number 1. It's very rare to say that, for every pound of normal force, there would be more than a pound of friction. Why am I saying pounds? I don't know. That's a unit of force maybe most of us are more familiar with. But for every newton of normal force, could there be more than a newton of friction force? There could be, but that's not going to be the scenario you see. All right? You will see any and every case fall into that category. So if you get an answer for a mu, whether it's static or kinetic, that's more than 1, you got to say, uh-oh, I did something wrong. There's probably an upside down fractional algebra thing in there somewhere. Okay, so those are good qualitative things, semi-quantitative things to know about coefficient of friction. Okay, here's an example problem. If you've never seen the Stonecutters episode of The Simpsons, you should stop what you're doing and go ahead and watch it. So in this episode, Homer is spying on his friends who are going to a secret meeting every so often, and he falls through the glass ceiling of this building, and they realize that he's the chosen one because he has the mark of the Stonecutters as a birthmark, and so he is made to drag the Stone of Triumph by a chain wrapped around his neck. It's a great little scene there, folks. So anyway, we want to figure out, with all this information, the coefficient of kinetic friction between the block and the... Oh, no, I'm sorry. We want to find the stone's acceleration. Okay, so let's draw a free body diagram for the stone. Oddly enough, that's how this starts. There's the stone. It seems there's a chain applying that tension force. There's the weight of the stone. There's the normal force exerted by the ground on the stone, and there's a friction force. And it's a kinetic friction force because this object is sliding. All right, we want to find the stone's acceleration. So we're going to say net F in the x direction. I'm going to go ahead and add components of t in each of two directions. I'll put this ty here. Sometimes I would put it over here, but I don't want to put it right on top of that normal force. Okay, and here's angle theta. And a net F in the x direction says Tx minus the kinetic friction force is max. Tx, we know we're going to write we're going to write as T cos theta minus, well, the friction force is mu kinetic times the normal force equals max. People that move too quickly will say n equals mg. That's always the case. Well, it's not the case here, because if we do a net F in the y, you will notice that n plus ty minus mg equals 0 because ay is 0. Even though this object is going to accelerate in the x direction, it will not accelerate off the floor or down through the floor. So therefore, those are equal. The upwards equal the downwards. So the normal force here is mg minus ty. And notice I drew my normal force a little small, significantly smaller than the mg force, because that's the real truth. This n is, well, whatever that number is. So now we can put that n into this expression, and we can see that T cos theta minus mu k mg minus T sine theta, well, that equals ma. So there's A. Okay, so substitute and solve. And if my button pressing is right, I think we get 0.26 meters per second. What say you? You say fine? As do I. Ooh, here's a great question that we'll get to next time. Some of these free body diagrams for things that are for which friction is an applicable force. Some of the free body diagrams, and therefore the solutions are tricky because they're so simple. All right, so this is a scenario in which if someone were to know how far that was and the kinetic coefficient of friction between tires and road, that's all you need to know to figure out how fast this maniac was going after it. Oh gosh, ran over a bike. It's okay, it's just a bike. And then came to a skidding stop. So you can do some like forensic analysis with this mu case stuff, and people do that for a living, some of them. So that's a topic or an example for another time. Okay, thanks folks.